to the Design for Serviceability talk. My name's Michael. I'm one of the mentors on 971. As a job, I work at Intuitive Surgical as a new product manufacturing engineer on our robotic surgical instruments, which are very hard to manufacture and assemble, and so a lot of those things transfer over into serviceability. So I will be helping out in this talk, and we also have Lara.
Hello, I'm Lara. I'm one of the students involved in mechanical on the team. During the season, I was the subsystem lead for the climber, and on our third robot, our off-season project, I'm subsystem lead for our intake.
So we'll get right into it. Lara, you want to start with the overview?
Yeah, so an overview of this presentation, we're going to start off with what is design serviceability, just a basic overview on that, and how does it play into broader goals in your teams. And we're going to do a case study on our 2022 robot buckets and a detailed breakdown of our approach to design serviceability. So starting off, what is DXF? This is designing for excellence, and how it applies to FRC is all these different focuses. In a robot, we build the robot for things that you probably know of. We design for performance, doing well in competitions, for controllability, making the robot do what we want it to do. Design for reliability, consistent performance, and then we have the other three. Here I have less. This is designing for manufacturability, designing for assembly, and designing for serviceability. In this talk, we're going to be focusing more on the latter three, manufacturing, assembly, and serviceability, with the main focus on serviceability and its ties to manufacturability and assembly. So for more detailed breakdown, design for serviceability, key decisions here are having a plan for replacing parts that we think might break just through the wear and tear of a season, any collisions, things like that. Then we go to maintain it, build like subsystems and sub-assemblies, things you can swap out, quick changes you can make in the pit during like the heat of a competition. And you have access holes. In order to make these changes, you need to be able to get to all these bolts and things like that. So that's really important when designing. You know where you're going to be putting these bolts, nuts, things like that, so you can actually get to them. Design for manufacturing, using the least time possible, and then simplifying, combining, eliminating parts is really important in order to do so. You have reducing like the necessary skill. You have your whole team that can work on making all these parts, and you want to make sure you're optimizing where you're using those resources. So looser tolerances are a really good way of making parts more manufacturable. Then you have design for assembly, which is minimizing like the possible mistakes. Poka-yoke is one term. You want things to be symmetrical when possible, just so they can't get mistaken and put on the wrong side. And then you're reducing the interdependencies. If you have things waiting on other subsystems, that just slows down the entire process.
So I think that serviceability is one of the most underrated metrics that teams design for in FRC. And there are a couple reasons why it's so important and why it really is a game changer in how well you're going to do during season. I think the thing that is most applicable to all teams is that more serviceable robots are easier to iterate upon and make changes to. So as the season progresses, you can get better and better. You can adapt to the changes in the games, how teams are playing the game, and you can continue to improve easily because your robots are easy to change. Also, really important is that not all time is equally valuable. For our team especially, but I think most teams agree with this, time at competition and on the practice field, any time when you have access to a field, it is worth way more than time at your shop back home. And so really taking advantage of that time and using it to its full value can really be a game changer for how teams are able to perform. You're able to do more drive practice, get more testing on your mechanisms, as long as your robots are serviceable and easy to maintain and keep working. The last thing that's really incredibly important when you're trying to take a team from, let's say, the 90th percentile to the 99th percentile is how you guys are going to do in eliminations. So on-field robot reliability is often the decider of matches and eliminations. I have this metric right here. So as you can imagine, if you have two evenly matched teams or alliances in eliminations, there's really a 50-50 shot of you coming out on the other side and being able to progress. If you lose one match because your robot wasn't working, or you weren't able to get the robot ready or a mechanism ready for that match, that takes you down to 25% chance of advancing in eliminations for that round. And so that's really just straight up halves your chance of advancing. And so being able to have a working robot in every single match in eliminations really can bring you from one of the top teams to the highest teams in FRC. DFA and DFM, as many people know, is also really important in FRC. So that's design for assembly and design for manufacture. So I think everybody knows pretty well that time is really your most important resource. It really is the biggest constraint in FRC. We only have 6 weeks to build our robot before the game season starts. And so taking advantage of those 6 weeks and any time you have is incredibly critical. So one reason that you want to design parts that are easy to manufacture and design assemblies that are really easy to assemble is that there's often duplicate parts on your robots. So for example, a really common one is left or right side parts. We also had 2 intakes, for example, on this year's robot, so a front and a back side. And so any change that you can make to one of those parts or assemblies is multiplied by the amount of times you have to do that on the robot. Also, redoing work costs a lot more than doing it right the first time. At the very least, it costs 3 times the amount of time because you have to do the work the first time, undo it, and then redo it again. So doing more things right the first time really incredibly reduces the amount of time you're taking to build your robot. And another thing that's really important is that bad DFA and DFM disproportionately affects your most skilled team members. So most teams have those students that are best at machining parts, best at assembling parts, and so if they have to be the ones machining every single part on the robot, it really creates a bottleneck for your team. And so designing parts that can be machined by less skilled machinists is an absolute game changer. And it also designing parts that can be done on lower accuracy machines. For example, taking CNC parts. For example, on our team, we have a CNC router. And being able to move it to manual machines or drill presses, simpler machines, can really remove that bottleneck that is often limiting teams and preventing them from hitting their deadlines. Also, if you have parts that don't fit, there's a lot of time spent trying to modify them or file them to get them to fit, and often you're having your most skilled students being the one to do that because they're the ones who designed it, who know how it's supposed to fit, and also just improving your ability to manufacture good parts increases your yield of good parts and reduces your wastage. So those are all really important reasons why you should be considering these things to make your team better. So kind of getting into like the real details of like what can you do specifically that will make your robot more serviceable, more assemblable, more manufacturable. I like to have, like this matrix, I think really drives home the idea that a lot of this is about trade-offs. And quite critically, like on this matrix, there are like the green check marks represent things that benefit manufacturability, assemblability, serviceability, and also performance. Sometimes you can make a change that benefits those things and also benefits your performance. So when I say performance, I'm talking about reduces weight, increases reliability, makes your robot easier to program or more controllable. the best things you can do are the things that it's a pure benefit across the board for performance, manufacturability, assemblability, and serviceability. But sometimes there are things that benefit a couple things and hinder one or two of those things. So these things are, this list on the left is really the main things that I think all teams should be looking at because it affects multiple of these factors. So the one that people probably know best is simplifying your conceptual design. I think people really know that you want to build simple robots. That's something that's often repeated, and you can see exactly the reason why here. It benefits manufacturer, assemblability, and serviceability, and there's no hindrance on performance. So that's why people always talk about that. But the ones below it are sometimes less often talked about. I think combining parts is really effective. So if you take two parts that you would have to make otherwise and combine them into a single part, there's benefits for performance. A lot of times it's stiffer, or if maybe for the same stiffness, it can be lighter. And it also really benefits assemblability because you don't have two parts that you need to connect to each other anymore. That said, it can also benefit or hinder manufacturability. If you have for example, on our team, we CNC route our parts. We have to cam our parts. And so because of that, oh, sorry. Yeah, so on our team, we have to CNC route our parts, so we have to cam our parts. So if we take two parts and we combine them into one, that reduces one cam step. Sometimes it can make manufacturing more difficult, especially on like for manually manufactured parts. So like mill parts or lathe parts, it can make the part more complex. And then sometimes it also hurts serviceability. Because sometimes you will break that part and now you have to replace a larger part. I think another really big item that teams should be considering when they're looking at these trade-offs is eliminating parts. If you can get rid of a part, it's pretty much always better than having that part there in the first place. It benefits performance because it's lighter weight. It benefits manufacturer assembly and serviceability because you don't have to make that part anymore. You don't have to repair that part anymore. You don't have to put it on the robot. Another item is changing part material thickness instead of adding lightning holes. I think teams commonly run into weight issues, have to lighten their robot, and so if you consider alternative materials or alternative thicknesses of materials, it means that you don't have that extra op when you're trying to machine a part of cutting out weight. Using duplicate parts, so like I was talking about left or right side parts, sometimes you need to have unique parts for weight reasons, but if you can keep the left side identical to the right side, it eliminates another part that needs to be manufactured, that needs to be assembled, or it makes it easier to assemble because it's identical on the left or right side. And it's more serviceable because your spares can be used for either side. There's also a Japanese term called poka-yoke, or mistake proofing, which means that you design things in a way where it's impossible to assemble incorrectly. So we'll get into detail a little bit more in depth later in the presentation. But if you can design a part so that it can't be assembled incorrectly, then you've eliminated that possibility of having to rework a part, having to undo your changes, undo your assembly. Access holes are really helpful because they allow you to assemble and service your robot. Though they do cost some manufacturing time, usually that trade-off is worth it. And then replaceable sub-assemblies sometimes can add weight, but often makes things parallelizable. So two people can be working on different sub-assemblies, and then the only step at the end is to combine them together. So that's kind of, I know I went through a lot of things there, but we'll get into a case study in a little bit that will kind of walk you through that in more detail. But this is a matrix that I would kind of keep on coming back to as a team when you're trying to improve upon these things. So again, we're going to get into a case study in a second of our 2022 robot, what we did to make that robot really serviceable. And so As we're going through that case study, it would be really great if you could think of these golden rules and think about what was going through our minds related to these golden rules when we were trying to design the robot. Like the last slide showed, DFX is all about trade-offs. You're trying to maximize benefits, minimize costs. That's really what it comes down to. But that's obviously really hard to do. It's really hard to always get the benefits with none of the negatives. And so the way you do that is by treating each opportunity, each design, each mechanism as completely unique. There's a lot of details that are specific to each mechanism, and by taking advantage of those and being really creative in how you're thinking about things, that is what's going to allow you to get all the benefits with none of the negatives. And really the most important tool to doing that is putting yourself in the position of the person who's going to have to make, assemble, and maintain your robot. And for most teams, a lot of times that's the same person that is designing the robot. They're often one of the more knowledgeable people on the team. And so by thinking about the trade-offs and how much work is going to go into those processes in the future, you can hopefully improve your ability to do these things better and continuously improve. So this is our 2022 robots, like we were saying, buckets, a case study of it. And there's a couple of things that we wanted to kind of put out there before we get into it. 971 really enjoys building complex robots. And a lot of times that's really we're really fighting our ability to design high performance robots, highly controllable robots, while also building robots that are serviceable, manufacturable, and assemblable. So on this robot, our goal was to optimize ease of serviceability, manufacture assemblability, while trading off minimal performance because we have that really high bar that we're setting for ourselves in terms of performance. But a lot of you probably build simpler robots than us. And so because of that, you can probably make robots that are way better, more serviceable, and more manufacturable than we can. And so you shouldn't take this necessarily as the golden example of what to do, because you probably can do even better of a job than we did.
All right, so starting off, I'm going to roll this to the center so you can see this better. But this entire robot has the upper half on a turret. So in the turret subsystem, this is the least accessible because it's all at the bottom and we need to compact that. And our overarching design was to maintain as much serviceability on this despite the space constraints. Move forward. So the turret gearbox, not very visible to you, but if you take a look at the underside, we have our battery underneath. It's a bottom-loading battery, and every time in the pit where we're changing out the battery, that's when we could check our turret, our belt tension, things like that. So we designed accessibility holes through the base of our robot, utilizing the battery door position.
There are also these small access holes, so you can see kind of in this right corner is our turret gearbox. And so being able to maintain the motor, possibly remove it if we need to. There are also sensors involved. Those access holes are designed into the belly pan, but are what allowed us to be able to maintain that gearbox, even though it was at the bottom of the robot and hidden by the belly pan.
So if you take a look at this, you have these different boxes. That box A, that is our belt tensioner. And we had a ball and Allen that we were using to tension that, as well as a notch in our wood that allowed us to access this bolt. So this bolt is hidden in the notch of the wood. This allowed us to keep the same amount of performance because we have a cable carrier running on the wood up top, so we wanted that to be completely flat. If you take a look here, you have C, this is our sensor. So we want those to be as accessible as possible, so we designed a separate sensor shaft on that in order to keep those in a more accessible position. And if you take a look over here, this circle right here, that's our motor. And then it is completely accessible on the top. It's right here on the robot. And it's accessible from just the upfront face. And you just rotate the turret and you're able to get that out.
Yeah, so you can already see some trade-offs here. There's an extra op for that notch in the wood that requires extra manufacturing time. There's also this completely separate shaft that the sensors are attached to that we 3D printed. So there's completely extra parts, but we made that trade-off for serviceability. So again, you're already seeing right here how, because this was the least serviceable subsystem, we were having to make trade-offs for manufacturability and assemblability so that we could gain serviceability.
All right, so this is the cover plate. We use wood on our robot, and we're proud of it. This is because it's a combination of it's easy to machine, it had the stiffness, and it had the low density. And that's why we chose to use it here. It served its purpose and did that well. And as I mentioned earlier, this motor right here is removable from the top. So access holes, there's a lot of them. You can probably not see it from here. This is probably a better image. But all these holes are access holes to the hardware underneath. So anything we want to remove, tension, anything like that, we're able to access through the plywood.
So moving on to the intakes, our robot, as many people know, had 2 intakes, and because we had 2 of them, they each needed to be lightweight. However, they also extended outside of the frame perimeter. So that meant they also needed to be robust, but also importantly, easy to duplicate because we needed spares, easy to replace because they were likely to get broken from running into other robots or parts of the field, and easy to repair once they were off the robot. So the overarching design goals were to maintain our ability to manufacture them and assemble them because we would need so many, while also keeping weight low. So the front and back intake designs are actually identical. There is a high weight cost just from having 2 intakes, but we were at least able to maintain the complexity cost otherwise by keeping them identical. So that meant we could reduce the unique parts that needed to be cammed, designed, manufactured. There weren't separate front and back intakes that needed to be individually manufactured. They were all the same. There was a single assembly process that students could get good at, and that reduced mistakes because we had experts in manufacturing the 1 intake design that was going on the robot. And it also meant that spares could be used for either side. So we could make less spares. We didn't have to make, let's say, 2 spares. We could have 1 spare that could serve as both a spare for the front and back of the robot. One really cool thing about the intake is that we have 2 ways of servicing it. So the entire intake arm can be replaced. So this is a really detailed view of a cross-section of the pivots. So Lara, if you could just point to where the pivots are. There's one on the left and right side of each intake. And so we have this bearing setup that where we have a single very small shaft that can be slid out, but actually also allows us to preload the entire stack up. So you can see there's spacers in between each of the bearings, in between the plates of the tube, and so you can actually get preload on that entire stack up, make it really stiff, but also means that it's 1 screw to remove and the entire pivot slides out, or 2 pivots, 1 on each side. So the entire intake arm was removable. The entire intake uprights were also replaceable. So in case they bent backwards, which we did probably have to do, I think only once, but maybe we had to do it twice, replace an entire intake upright. So there's like around 14 screws all along the perimeter of the drivetrain, but it was designed such that we knew we might needed to do that. When we needed to do that, we were ready, we had a spare. We were able to do that relatively easily during breaks between lunches or after matches ended for the day. This is our drivetrain transfer. So it was the mechanism or rollers that moved the ball or held the ball in the drivetrain and then moved it into the catapult when we were loading the catapult. So again, there's 2 of them. So we wanted to make them easy to manufacture because we would have to make so many of them. One thing we're able to do here is make both that big right and left plate identical. So even though there's a roller gearbox on the right side only, there's no matching gearbox on the left side because one motor drives the entire system. We left in all those holes on the other side even though they were unnecessary, it meant that we didn't have to cam another part, and we would never mix up the right and left side part either. So those things made it easy to manufacture, easy to assemble. The next thing is the intake rollers. So in addition to making the entire intakes replaceable, we also wanted to make individual rollers and the mechanism wheel roller replaceable if possible. So on all of these, the rollers are made in a way of using dead axles. So what that means is that there is bearings actually in the side plates, but there's just these small removable shoulder screws at the end of each roller. So you pop out those two shoulder screws, the entire roller pops out. We also tried to use West Coast Products Versa roller components, in particular on the transfer rollers. So cost parts are always better, means there's not a part that you need to manufacture. So if you can use cost parts, that's always better than using a custom part. The last thing that I wanted to talk about is the chain tensioners and ball ramps. So you can see on the right here in pink, there's these two small holes. So on the right side, that screw was is one of the two tensioner screws, very easily accessible, but the other one is hidden on the inside of the tube. So we have this access hole that allows us to very easily stick an Allen wrench in and tension that other side of the tensioner so that it would be balanced. And the other thing is we have these ball ramps. So all our electronics are on our belly pan. We wanted to make sure we still had access to the belly pan. So having these really small ball ramps meant that our electronics were still accessible instead of having like a large polycarbonate plate or something like that. And also there was like two fasteners that we could remove and pivot out the ramps for completely unfettered access to our electronics.
All right, so this is the case study on the climbers. 971, we have a history of putting the climbers on at the very end of our designing. So in 2016, we did this thing where we designed without a climber, and we're like, if we have time, we'll add a climber onto this thing. Kind of the same principle here. This was more thought out. We started with designing it, but throughout the design, we knew we were going to be the last subsystem on the robot. So that meant we need to be modular, so we wouldn't hold up the progress and the time on practice fields and drive practice. So this was a design for iteration. We started off with a very simple mid-bar climb and plan to continue towards a more complex climb later in the season. So these are the climber extension tubes. They were entirely replaceable. This is the entire subsystem right here. We just stole it off the robot. It is like a couple rivets and you put this entire thing in. It's really modular, and we mounted it onto the mounting frame of the turret, and going through this, it's a chain assembly, and we don't have a friction brake or anything like that. Reason was we took those out because those are additional parts. My bad. Those are additional parts that meant more time, more variables, more things to continue to maintain. So we did the math on the gearing. We did the math on the gearing, and we made sure that our robot would not fall down. We used high gear ratios. It would just stay on the bar. It was like 18 seconds it would take us to fall from the ground, and in a competition, the scores counted within like 5 seconds. So we had plenty of margin there. And then we were using COTS parts like chain tensioners, West Coast Products, and the gearbox was a Versa Planetary.
Yeah, so like we said before, one of the best changes you can make to DFX is completely removing a part, because again, you lose the weight, you lose the need to manufacture the part, you lose the need to assemble it onto the robot, and you lose the need to service it. And so this friction, the lack of the friction brake or ratchet that a lot of teams ran is a perfect example of that. It meant that we didn't have that part that could break, didn't have that part that we needed to make. So with the frame, we used epoxy.
onto the robot, as well as rivets. So this took away the need for welding, which could have led to warping, since so many things were dependent on this entire structure. We have gussets, and one of our constraints that was pretty major during the season was weight. We had a lot going on with our double intakes and all this frame structure, so we wanted to reduce weight where possible. So instead of running a 3/16 gusset plate, we brought that down
before any parts get manufactured. So on our team, we have a group of mentors that are able to do that, but if your team doesn't have mentors, you can also have the most experienced student be the one to do that. Just somebody other than the person who designed it, who is able to see possible changes or possible improvements that could be made to improve all of these aspects of the robot. We also design mechanisms to be robust first and serviceable as a backup. So better than having to service a part is it not needing service in the first place. So again, we oftentimes struggle with this because of the weight limit. It's the easiest way to make things more robust is adding more weight into them. And so because we're not, a lot of times we're not able to do that, we had to make them serviceable as a backup. But maybe on your team, you are designing similar robots with less mechanisms and have more weight. And so the best thing you can do is make it robust, and then you don't even have to worry about serviceability. Also, the more likely a part or a subassembly is to break, the more effort that we and you should be spending on planning for serviceability. So for example, I like to point out motors, sensors, rollers, wheels, all of those should be easily replaceable, and you saw aspects of that on our case study. The sensors on the turret were replaceable, every wheel and roller was replaceable, the turret motor was replaceable, despite how hard that was to design into our system. Also, mechanisms that extend outside the frame perimeter need to be more replaceable than other mechanisms, and ideally as a subassembly. So on this year's robot, that was the 2 intakes. So again, we had multiple ways to service them, both making the arm removable and making the entire uprights removable. Also, try to place fasteners and tensioners in accessible locations or provide access holes if that is not possible. And again, make subsystems removable. It's way easier to maintain a subsystem once it's off the robot. There's a limited amount of people that can be working on the robot at any single time. So being able to take the subsystem off and work on it then, especially like if you're in the middle of drive practice and let's say the climber breaks and you're not using it for drive practice, just take it, if you can, just take it off the robot, fix it off the robot, allow drive practice to continue, and then put it back on the robot when at the end of drive practice. Next, we're going to go into some of these principles for assembly and manufacture. In particular, in yellow are the things that we kind of haven't covered yet, and so far is going to go over that.
So we review the design. Something we mentioned earlier is mentor review. Like for our off season, we have our more experienced students reviewing design, and then designing mechanisms for smaller sub-assemblies that are modular and easy to put together. And then that can be worked on in parallel. And this is yellow. This is parts are nearly symmetrical. We want to keep things like as symmetrical as possible so they don't get mixed up. If you put the plate on the wrong side, epoxy on the wrong side, now you have a kind of issue there. That is something you'd like to avoid. So if they're the exact same part, it doesn't really matter where you put them. And that is so, or clearly asymmetrical. If you don't have the weight to make two things completely symmetrical, make sure that they look significantly different and it's not just one hole that is making or breaking that side. And duplicate parts, same thing as above, making sure you're duplicating when possible versus having unique left-right designs to prevent misassembly if you have the weight for it. And then the last one here is if there's like room for a nut wrench, you want to be using nuts just so you have the option of torquing from the back and preventing cross-threading and like tapped holes. This is especially like if you have space to place it and it's not just like in a really inconvenient spot, is optimal. Shapes. There's very big differences. If you put this on backwards, your center to center will probably be off. If you can keep them symmetrical on both sides, you can rotate it, or one side's clearly longer than the other, that's going to work out a lot better. So we try to use and use or modify COTS parts as much as possible. That way there's less pressure on our machinists. We consider alternatives before lightening. Like on this climber, we have 40 thousandths of an inch aluminum. Just it's an air tube because that's what we needed for that space. Slide before, nuts are preferable over tapping. You don't run the risk of cross-threading and then ruining that part. And then design for as many parts as possible to automated manufacturing processes. We take a lot of our parts are using a 3D printer, so that takes it on those machines. 2D tubes, 2D plates and tubes that can be cut on the router for us, or if you have other automated machines. And then duplicate parts, and then 3D printed parts. Think about the supports. That's something important. You don't want something that's like going to have levitating parts.
Mm-hmm. And a lot of times you're going to have to print the support material anyways, so you may even consider just like essentially adding material where the supports would be anyways, because you're going to have to spend the time on the machine printing that material anyways, and it might make the part more robust. Yeah. So how to get started as a team on this. So the first thing is decide as a team which DFX principles will help most in achieving your team goals. I think serviceability is a great one to start with because I think it probably has the biggest effect, biggest positive effect on the success of your team. But if you want to bite off all of these, go for it. Just try to figure out what goals you as a team want to achieve and what will drive your team to success. Then you need to make sure the entire design team understands the value of your DFX goals. You want everybody to be on board, everybody to be working together. You want people to understand why it's important, what they're doing, and the way they're doing it. Next, I would set up an official design review process for approving parts before manufacture. Like I was talking about previously, on our team, that's a group of mentors that are able to approve parts for manufacturing. But if your team doesn't have that, you can also have experienced students that weren't working on the design process be the ones to help in that approval process. And you also need to only accept attitudes that are open to constructive criticism during this process. The goal of this is to make your team better. You guys started out this process all together agreeing that working towards these goals would lead your team to on-field success. And so you guys need to be really clear that we as a team are working on this, and we as a team would like these things to improve, and we're not going to accept anything less than our best efforts to do well at our goals. So are there any questions? I know we went through a lot of things. I've left up this really important kind of like matrix that I think summarizes a lot of the things that teams can do and the trade-offs involved, but we would love to answer any questions you had during the course of this presentation.
I had one question.
Yeah.
You mentioned that like you'll have a group of kids be super good at making one
Assembly?
Sub-assembly. Is it really better to only have kids who know how to do one thing?
Yeah. So yeah, I don't think it's better to have kids who only know how to do one thing. It's better to have well-rounded students, and that's what we strive to do. But even if, like, you can imagine, like, just there is one person that is assembling or experienced in assembling the intakes, even if it's yourself, you can just imagine that if you have to do the same process every single time, it means that you're going to make less mistakes. So not saying that you should have, like, you should kind of limit what students are doing, just that you should be designing things in a way such that the people that are doing those tasks will make mistakes when they're doing that repeatedly.
And I think just to add on to that, we're not having the students do the same thing over and over again. Even though it's the same process, there's multiple elements to it. We shifted recently to a different leadership structure. We'll be talking about it later. But the entire subsystem, you go through all the manufacturing parts. There's like lathe parts, router parts, all that needs to come together. So they're learning all those skills in kind of the bubble of that subsystem, if that makes sense.
How do you view the kind of balance between like speed and really optimizing for DFX? Like for example, I really like your shoulder bolts on your intake going into those hubs. That's a really clever solution. But if we were to do that, then we would probably have to custom order those shoulder bolts and bearings, and that would slow down our whole process. So then it's like, well, we could also just do live axle with half-inch hex, and we have tons of bearings. So like, how do you kind of balance that?
Yeah, so I think as a team, we like to solve a lot of problems in the design process. That isn't necessarily what every team should be doing. You have to really decide what is best for your team. So it sounds like for your team, it might, especially if you're like up against hard deadlines, like a competition coming up, it may make sense to like just use what you have and just make that design as serviceable, as manufacturable, as assemblable as possible, given those constraints. But in general, it goes back to the idea that saving a little bit of, like spending a little bit of time in the design process often can have much larger multiples later in the season. So we often have like, McMaster orders are the easiest. If it's a McMaster part, it often comes 1 day, 2 days at the max. And so that's a really easy decision to make. Even West Coast Products parts, a lot of times will, like, we know it's going to come in the next week, and so we'll make that trade-off and decide to go with the COTS parts, especially if we can foresee it earlier in the season.
Thank you.
Yeah.
Do you guys have a formal system for practicing, like, replacing parts in the robot beforehand?
Lara, you want to talk about that?
Yeah, so I was on pit crew during the season, and in order, like prior to competitions, you want to go through your checks. So for me on climber, that was like checking the tension. You want to know what that felt like prior to the competition. And the people who are working on it need to know like the tools in order to replace them. So say you are doing the intakes, you want to make sure you have all those tools, and that's also part of our process in packing. So in packing, you need all the tools to do these shifts, so that's why you take a look at it prior to the competition. So we'll have, on the same day we're packing, we're taking a look at our assemblies. Usually people who are in pit are the people who have designed it, so they have experience in how it works. Does that answer your question?
Yeah, I'd add a little bit onto that in that for specifically this robot, we're not proud of it, but we had to change intakes quite a bit. We actually often ran at least a second intake. We swapped to a second intake right before eliminations at the very least at pretty much every event we went to. Just because of the design, there was nothing we could really do about that. And so, especially before champs, when we were taking apart the robot, when we were taking apart sub-assemblies and assembling sub-assemblies in preparation for spares at champs, we were making sure to have the pit crew do that because we knew we were going to have to do it in a competition. We treated it as if it was drive practice for the drivers. We treated it as practice for the pit crew in practicing the thing that we knew they were probably going to have to do in the middle of competition. In the back?
Related to the previous question about sort of speed versus optimality.
Yeah.
Does your team go so far as, for example, designing in fasteners into the CAD if you put the bolts and the nuts in the CAD itself?
Yeah, so we try to do that. Again, tight time constraints, everybody knows what an FRC season is like. So we try to do it, especially if you have, we switched over to Onshape this past year, and so we had really good engagement with CAD, and so it was really easy to find people that could do those small details that were necessary. But sometimes when it's like 2 days before competition and we're redesigning a mechanism, that doesn't end up happening. But we try to if we can.
Is the on-shape, is that allows you to have more people working on the assembly at the same time, or is it
Yes,
okay.
exactly. And there is also a presentation later today talking about our strategies for using Onshape, because there are some pitfalls there too. So that's a good presentation I would recommend going to if you're interested in that. Yep.
Yeah, I was gonna ask about how you guys deal with essentially pit drive team communication. So like, I'm assuming you guys probably have a pit checklist for this robot,
Yes.
but also like coming out of a match, if you had a catastrophic failure happen, how would that be communicated to the pit crew?
Okay, I can answer this. So I've been part of both sides of this. I've been on drive team in off season last year and on pit crew. So how it worked is drive team focused on driving. We want our drivers to be completely focused on that. We have our pit crew watching in the stands what goes on, so the most catastrophic things they will notice. But if there is something drive team notices, they just let the pit crew know, and then they go and watch their game video, and they're not really involved in the repair process. But from there, just from the information from the drive team, they're able to make those changes. We have the same functional, so we look over all the subsystems every time. Even if it was a perfect match, nothing went wrong, we double check everything. And kind of, if you're a pit crew member, you run the cycle of you're in the pit when the robot's in the pit, you're on the field when the robot's on the field. That way you're seeing what is happening throughout the entire process.
Yep. Yeah. So Lara exactly nailed that. Just to add on a little bit of detail to that, we hold our pit crew to pretty much the exact same standard as we hold our drivers. They're expected to have good sleep. They're expected to go to bed early. They're expected to always be where they need to be, whether that's ready in the pit when the robot arrives, or on the field when the robot is competing. So again, pit crews, or not necessarily on the field, in a limb, sometimes on the field, but at least in the stands, watching. So if it's like a minute into the match, we see a mechanism break, we'll already send the pit crew back to the pit to start getting what needs to be fixed ready. And we're very well practiced at that, and practicing that in qualification matches allows you to execute a lot better in eliminations, and we really try to express that to our pit crew.
Yeah, and we often do kind of a talk on the way back. So as we're walking back, we're talking through, okay, this is our game plan when we get back to the pit. And that's where we're organizing our approach. Yes.
When you were talking about the turret, you guys talked about how you had one axle for the turret and then a separate axle for the sensors.
Yeah.
Can you explain that a little more?
Sure. Yeah, I can wind back. Yeah, so so you can see in black here, that's a 3D printed mount, and there's a shaft going through that. So there is an encoder, a mag encoder on the top, and then there is a pot on the bottom. So the pot's actually hiding the pulley, but there is essentially a pulley going that's right there, right underneath the pot in that view. And then there's a belt that's not in CAD, but it goes between this shaft and that pot. So it just couples kind of the output of the gearbox to a separate shaft, such that we could place that sensor shaft in a place that was a lot easier to service, and I had both our encoder and pot on it. I know a lot of teams only run one of those, but we run both. Both of those. One sensor was on the bottom, one sensor was on the top. Does that answer your question?
Yes.
Cool. Sure.
What was the benefit of having both? The mag encoder plus a pot, couldn't you just read the same values from both?
Yeah, so we use the pod as kind of a zeroing mechanism. So it allows us, when the robot starts, so the mag encoder is relative and is higher, it's able to measure a much finer precision, especially because a lot of times it is earlier in the gearbox production. So it's not visible on the turret here because we didn't do it, but a lot of times the pod will be closer to the output, so there's less backlash between the output of the system and what the pod is measuring. So it's measuring really good absolute precision, and then we have the encoder that's measuring at a much like higher precision that we can use so that all our sensor feedback and control loops are really smooth and have a good idea where the system is.
I see. So the gear ratio works out so that the precise position of the turret can be determined from the potentiometer reading, but it's geared such that you couldn't determine the position of the turret from just the absolute rotation of the sensor shaft.
Yes, in particular because the mag encoders are only designed for 360-degree rotation, and they're also relative to where they start up at, or I guess actually they're not, but yes. But if we wanted to use a sensor, that we also have the option to use non-mag encoders. So it's really the combination that allows us to get like the ability to start up the robot and not have to like zero any mechanism either mechanically or encode the moment the robot starts up. So the moment auto starts, the robot knows exactly where every mechanism is without zeroing, and because we have the mag encoder that itself has higher, like lower noise really is the main deal, and higher precision than the pod, get really accurate understanding of where the system is.
And this was really for serviceability, because you could have moved the mag encoder to the direct shaft of the turret and accomplished the same thing.
Yes, exactly. Yeah, we may have even gotten slightly less backlash. There's very little backlash in the transmission, like in a belt transmission, but may have gotten slightly better performance in that sense. But we decided that, again, because the system was so hard to maintain, it was definitely worth that trade-off there.
Interesting, thank you.
Yeah.
Go for it.
Sometime at the end.
Yes.
I was curious if has it done anything in terms of trying to formalize both the design process and the design review process, having sort of checklists or things that designers who maybe aren't experienced with either the design process or the review process can kind of review and go over themselves without having to talk to a mentor about.
Yeah, so I'd say like in general, again, we have, like, I think Lara would be better talking about the exact structure of our team, but we have sub-assembly leads that are in charge of each subsystem. So they're kind of the student that should have the best understanding of the subsystem that's being worked on. And they're really good at delegating tasks and figuring out who to assign like different smaller tasks to, and kind of overseeing the entire process. But they're really constantly talking to the subsystem mentor that they're paired with.
So I can talk about this. I came into build season. This is the first robot I worked on as a subsystem lead for it. And through this process, you had our design like metrics and how complex we wanted the subsystem to be, as well as we had our parts list. Our parts list did more than just saying like, okay, these are the parts we're making. It also had like checkpoints of like we have our drawings, we have our manufacturers, we have who's manufacturing it, and we also have our season schedule, which tells us the deadlines for different checkpoints. So that's all in like a master schedule with the points in which like we're finishing CAD, we're finishing manufacturing, assembling, things like that. And then, yes, go ahead.
Just say, did you do anything to sort of, it sounds like you're relying on mentors and senior students to have a lot of the knowledge about how to do this stuff. Do you do anything to try to document sort of institutional knowledge instead of just kind of passing it from one person to the next?
Yeah, so I'd say Spartan series is probably one answer to that. It has videos that we can reference, like as you can see we're recording, so we can have students reference those videos when we notice something. We may go, look at this video, this is like, tells you exactly how we would recommend designing this. So I'd say that's the main way. We also have some internal presentations. I think there's generally like weekly presentations put together by students, trying to, especially in the off season, trying to teach the rest of the team good practices, how we operate as a team. And so we kind of cycle through topics and try to hit everything we can.
Yeah, in the last 2 years, we've had a lot of recruitment to the team. So we've strengthened our onboarding process. and less so directly in like we go first for a broader approach because these are new students. We tell them like these are the different things, like here's the basics, the high level of each of them, and then from there you dive into more like specific trainings, like your tool trainings, your machine trainings. Like if you're going more mechanical pathway, you have your design for like CAD. We have like all the way up to like design challenges on that, along with a self-paced tutorial right now that we're going through. And that's how we onboard new members, and then it just, you kind of like work your way towards more experienced positions. And you work with, we have a really good mentor to student dynamic during the season. It's more paired with like a mentor and a lead student for each subsystem. In the off season, it's completely student run, student checked, but with the mentors there for us to get like a final design review to make sure we're not doing anything all that chaotic.
Any further questions? If not, we can break for lunch.
Okay.